Well, hello everyone, and welcome to the Launchpad. My name is Zach Aubert. I'm the founder and CEO here at the Launchpad Network. And here at TLP, it's our mission to inform and inspire the explorers of tomorrow because we believe that space is better together. And today I'm joined by Devon Papandrew, the Vice President of Business Development at Stoke Space. Stoke's mission is to lower the barrier of access to space with the full reusable launch vehicle. Devon, thanks so much for taking some time with me today.
Thank you, Zach. It's great to be here.
So Stoke Space development has been just in the last couple of years, but has been at an incredible pace. I know we got a lot to talk through, but before we jump into kind of the plans for your rocket and the Hopper 2 hop you just did, can you share maybe a little bit about who Stoke Space is, what your mission is for those that maybe haven't heard of you?
Sure. Well, our sort of core thesis is that if you want to be successful, you have to think about the end game, and sort of start there and work backwards. And at the founding, our two co-founders, Andy Lapson and Tom Feldman, sort of said, like, what's the future going to look like in 2035 or 2040? What is access to space going to look like? And then from that, how can we design that future now in a way that makes sense? And it was evident to them that that future was fully and rapidly reusable rockets flying to and from space, delivering cargo on a daily cadence. Almost boring, right? Like in the same way that like a FedEx 737 going all over isn't super exciting. It is when you think about it, but it's become so routine that quickly we're bored with it. And we said, well, how do we build the rocket, the launch capability that unlocks that future? And that's really our vision: is to streamline and scale the space economy, and that really starts with fully and rapidly reusable rockets.
And you're looking at reusability of not only the first stage, but also the second. And you've been looking at that from the get-go. That obviously points to that full reusable thing. Do you have a dream? You say once a day for each rocket, or just hopefully launching once a day with a series of rockets?
I think we want to design for the quickest possible turnaround time for each of those rockets for stage one to stage two. And obviously, stage one, we get back in like 10 minutes, right? It goes to space, deploys stage two, and comes back and lands at the launch site. Stage two, once it goes to orbit and deploys payloads, it hangs out on orbit a little bit longer, maybe a few days. And then comes down. And the design is to be able to land it a few days later at the launch site, quickly turn it around, maybe little or no refurbishment, just kind of refit, refuel, and refly. Um, but the goal is, to have our fleet of vehicles that we're achieving on average, maybe one flight per day, and that's certainly not in the near future. I think we have realistic expectations for the immediate future, but we wanted all of our design decisions to be focused on that goal of daily turnaround.
So we just saw the hop with your second stage for a test. Where's the first stage at? Where are you in development with that?
So first stage work has been ongoing, even in parallel with Hopper, and now obviously it's our main focus, right? It's the whole orbital vehicle that is. So our stage one engine, it's a full flow stage combustion engine, uses liquefied natural gas and liquid oxygen as its propellants. Full flow stage combustion is historically it's been considered a challenging engine cycle, and that challenge is not, we don't take that lightly, but we have a lot of top talent from around the industry that we've brought on board to help us do that. It's really if you think about creating an engine that is designed to operate, high efficiency and high thrust, but also low temperature and low pressure, it's clearly the right engine cycle. It's very efficient, can be extensible to long life, many reflights. And so we've done a lot of testing of the pre-burners. For instance, the Oxrich pre-burner, we've tweeted some photos of that in test. Turbo machinery is in work now as well. And we're tracking early next year a full hot fire of our stage one engine. It won't be super long duration, at least at first, but enough to get through the start transient, which is important to characterize that. And we're marching towards, throughout 2024, a lot of revisions and iterations and testing of that stage one engine. So that's the engine. Obviously, it's not the whole stage. Stage one, we're using a lot of the lessons learned and sort of manufacturing techniques that we've perfected for building Hopper and extending that to stage two. So the pressurized structures, so think propellant tanks, as well as unpressurized structure, which is all the structure that's not tanks. We're doing a lot of development of those manufacturing processes, right here at our headquarters in Kent, Washington. And we'll be sharing some photos of tanks and structure soon. Avionics and sort of the fluid systems are all progressing sort of right along as well.
So are you doing everything in-house then?
Most things in-house. Our thesis is that if you want to be successful in this business, you've got to be vertically integrated. So there's a few, I would say capabilities or one-off parts that we order outside, but most things we look to bring in-house.
It's amazing to hear you're going full stage combustion. There's only really been 2 or 3 engines with that. Raptor, the one that's flown, and then hopefully seeing you guys as the second. Why choosing going that route versus something else that's maybe more proven and maybe there's more experience in?
Well, it's a question the team talked about at length. I would kind of go back to, what I mentioned, thinking about, that future, which is, hey, we want a vehicle that's designed to fly 100 times and can readily, what we design today, even though, first we'll be doing some expendable flights and then maybe a couple reuses. We want it to be clearly traceable with minimal rework to that sort of holy grail, which is full and rapid reuse flying 100 times. And, if you look at other approaches, like if you look at a LOX kerosene gas generator, you're going to get a lot of coking, operates at higher temperatures and pressures. It means, is this going to be fit to fly on flight 2, flight 3, flight 10 without completely tearing it down and rebuilding it? And we said, yeah, that could be a fine interim step. But then when we really want to scale and achieve that daily cadence, we're going to recapitalize the company, start again on another engine development. That would be very hard to stomach, I think, at that point in our growth. So developing any rocket engine is hard. We have a lot of experience who have done stage combustion. A lot of folks here have done stage combustion, whether it's SpaceX or Blue or elsewhere before. So we said, why not leverage that great talent that we have here and actually just design for the end state today?
Absolutely. You talked about the first stage, but obviously the second stage coming back. But for the first stage's kind of return, what does that look like? Is it going to be similar to what kind of everyone knows with a Falcon 9 of an entry, burn, and landing to launch site, drone ships, both? What's that kind of reusable recovery look like for you guys?
Exactly. Stage one is akin to the Falcon 9, at least in that ConOps. So it's vertical takeoff, vertical landing, either downrange on a drone ship or return to launch site. And you take the performance penalty going back to the launch site, but that might be worth it because we don't have all that payload and we want to get our asset back quickly and turn around for another flight. That's the reason we start with stage two. Not that reusing stage one is easy, but as an industry, thanks to SpaceX, we've demonstrated that we've made it routine. And so we still have to go do that and build that capability in-house ourselves, which is certainly non-trivial. But stage two reuse really hasn't been demonstrated yet. And so we wanted to figure out to a high degree of certainty, at least what that looks like, such that we can flow down requirements and that knowledge of stage two down to stage one requirements, because those are, of course, stage one and stage two are highly coupled machines.
Right. I'm looking at that stage two, which is arguably kind of the most interesting aspect of your guys' vehicle. It's so different. It's a tapered design. It's got not just 1 or 2 engines. It's got it's got one engine, but a whole bunch of nozzles. Can you take us through just that design and how that unique design and system is going to help improve performance of that stage?
If the thesis is full and rapid reuse, obviously to bring back an orbital upper stage, it needs some kind of heat shield such that it survives atmospheric reentry. And if you look at traditional approaches like on shuttle, on Starship, those use ceramic tiles. Some of the capsules like Dragon or Apollo use an ablative material which burns off. And the problem with those like traditional reusable legacy approaches is they have catastrophic failure modes, right? As we saw tragically on Space Shuttle Columbia, a tiny crack that was due to a foam strike let a little bit of hot gas in, melted aluminum, and they had a very bad day. And what that drove then is those very, very extensive inspections of every single tile with X-raying and also visual inspection between each flight. And so we said, hey, if we're going to fly like a 737, we can't be inspecting 30,000 tiles on the underbelly of this vehicle between every flight. That's not operational reuse. So that was not a very attractive path forward for us. And then, early on, the team said, Well, we've been actively cooling rocket engines for decades as an industry, right? The combustion chambers, the nozzles, and those operate with passive failure modes. Rocket engines, I believe even the RS-25, the space shuttle engine, was fired with known flaws in the engine liner, and the cracks, the flaws, self-arrested. So we said, why not take this approach that's super robust and resilient to damage, and just spread it across the base of the vehicle? Um, why don't we just integrate that with the engine such that the engine and the heat shield are one and the same? And so we ended up with this actively cooled heat shield that was just part of the engine. And then we said, okay, well, that's awesome, but how do we like physically fit a heat shield and bundle it inside an engine in a way that makes sense and makes the engine perform well on ascent, but also the heat shield perform well and the vehicle be stable on descent? And through a lot of analysis, fluid dynamics, we identified this design, which is sort of this central plug from which we get some aerospike benefits, but that's sort of like a secondary happy accident. The goal is to just bury a heat shield in an engine in the central plug, and then thrusters sort of around the outside, and that's how you ended up with what you see today. And so we proved out that we can fly that thing and control it, obviously in the propulsive landing phase of flight with the hop. But yeah, it's also going to have really high in space vacuum performance as well.
Absolutely. It was amazing watching that hop. I know some people made jokes that it looks like it would have been a great demo for Burning Man. There was a lot of flame, but also really exciting to see it happen, because it's been a quick development to get to that point to see a hop test. You've moved on to looking at the first stage, but what's next on second stage? How does that development continue?
Well, there's a lot of learning that will roll in from that hop test. I think a lot of it may not be seen. The orbital stage 2 will look, in large part, quite a lot like this hopper vehicle, except it'll have a payload fairing and have a payload and all those things. But a lot of the internals, I think through that whole test campaign, there was a ton of learning. So hopper was sort of the cherry on top. But if you followed along on Twitter, we shared a bit about the wet dress rehearsals. There was a static fire of the stage. And through all that, we really honed in on our ability to do sort of launch operations to make sure that we get all the right propellants that are properly conditioned in the vehicle, all the right temperatures, make sure our turbo machinery works in a lot of different operating conditions. And that learning happened throughout the course of the process, not just at the hopper flight, like I mentioned. And so there'll be, some minor design changes that we roll into the orbital vehicle, but it's a huge sort of risk reduction, because now we know, like, we haven't flown into orbit, but we have flown this vehicle and we fueled it and operated it and gone through all those processes. So additional, I think, iteration would be fair to say on stage 2, but the main focus now is stage 1, because we need that to get to orbit.
Will we see more hops, or are you thinking there'll be that iteration, then eventually we'll just see some sort of test flight?
Probably not at this time for more hops. The goal was to get that experience and learning under our belts, but now we need to focus on getting to orbit. Getting there, demonstrating that we can do it, serving our customers, and doing a bunch more hops would be, frankly, a lot of distraction without a lot of marginal engineering benefit. So we got to focus on orbit.
So your second stage uses hydrolox, a propellant separate from its first stage. Quite interesting that you're choosing to use hydrogen, something most are kind of shying away from. Why use two different propellants for each stage?
Yeah, great question. Well, the main reason for choosing hydrogen for the upper stage is its cooling capability. If you want to reuse an orbital upper stage, every single kilogram of reusability is one less kilogram of payload. You take a 1-for-1 hit. And so everything that is required for reuse, we need to be somewhat, at least somewhat mass efficient on. And if you look at, cooling per unit mass by number of fluids, so, methane is another choice, which is actually the worst. Water, RP1, liquid oxygen, none of those are ideal fluids for cooling when compared with hydrogen per unit mass. And so that kind of was a clear we have to do this with hydrogen to do active cooling of the upper stage base heat shield. And there's some other benefits as well. It's very high ISP. So we get an excess of 400 seconds of ISP out of that upper stage, which means really meaningful capability performance to high energy orbits. So GTO, GeoDirect, TLI. That's been very interesting for both commercial and defense use cases. And then for stage one, why do we use a different fuel than the one we chose for stage two? It's really hard to make stage one close with hydrogen. Hydrogen, even when very cold, is quite fluffy. It's not very dense. And if you look at like Delta 4, very, very large structure for relatively small fuel mass in the Delta 4 stage one. And so, liquefied natural gas or methane, the industry has sort of been, consolidating on that as the fuel of the future. Comparatively, it's a lot more sustainable environmentally. You get high ISP out of it. It's great for reusable engines. You don't get coking like you do with Kerolox. So it's really just the right answer. Stage one and stage two are different vehicles. They're coupled, but they have different purposes. And fuel choice, obviously, is very relevant to that. So there's a little bit more complexity. That's true. We also, again, I kind of go back to talent. Like we have hired a number of folks who are, industry leading experts on working with liquid hydrogen. It's a very unique cryogenic fluid. And we've proven that we can operate with hydrogen. And I mean, we were test firing that stage two engine. I don't know how many times we fired that, many. And then of course, flew the stage just recently.
Well, it's unique because it kind of operates almost as one engine, but with all those nozzles. So you're actually proving out those nozzles faster than other companies where they have to test each one individually for it. Looking at the second stage, we've seen some of the renders you've released. How far are you into finalizing kind of some of the designs of fairing? Are you going Hungry Hippo? Are you going to recover from the ocean? What's that kind of all look like?
That's an excellent question. We've been going through those trades. Looks like we'll have a couple options. We'll have Hungry Hippo or the James Bond style where it opens up, remains attached, and then we're interested in downmass payloads as well. So maybe we capture something. And then we're also looking at large constellations and satellites who have sort of centered around the 5-meter fairing that's standard for Falcon 9, Vulcan, Atlas. I believe Ariane 5 is also a 5-meter fairing. And so we want to accommodate those kind of payloads as well. So we have a 5-meter fairing that early on is expendable, but I like to call it our separable fairing because it'll separate, but there's no reason we can't recover it in the ocean like SpaceX does, which would still make it reusable. So we have a couple options there based on mission needs.
And exactly as you ended it with, it's a mission need. It gives you more flexibility for your customer, which obviously is huge in this kind of ever-growing, more complex market that we're seeing. Once you have your rocket, you need a place to launch. Obviously, you're developing in Washington. In March this year, it was announced that Stoke was allocated Historic Launch Complex 14, Cape Canaveral Space Force Station. We saw John Glenn launch from here for his first mission to orbit, but we haven't seen a launch from there since 1966. What all has to be done for this to bring this pad back online, and how's the team feeling about getting such a historic pad as your first launch site?
Yeah, a lot has to be done. It's first of all, it's a huge honor that the Space Force has entrusted us with preserving the history of the Mercury program and John Glenn there, most notably, as well as sort of doing that legacy proud, right? We don't want to build up that pad and that capability and then not really leverage it to its fullest extent to serve U.S. interest in space. We hope very, very frequently in many launches. But it hasn't really been touched since the 60s. And it turns out salt air isn't too great for concrete and steel over those kind of timeframes. So right now we're working an environmental assessment with all the different stakeholders and parties there down at the Cape. And we've also sort of in parallel, we're doing a lot of detailed design of the layout. So where we're going to have our facility for the vehicle, propellant storage, the pad itself, where's the transport erector going to go, detailed designs, and what needs do we have for commodities and utilities. And the idea is that as soon as the EA is completed, which is hopefully in a small number of months, we'll be able to immediately pull the trigger and go. We have the construction team lined up to start actually building that. So we'll build up sort of the modern site, which is for our use, and then we're going to actually, in partnership with various entities down there, preserve some of the history. So there's an old blockhouse where mission control used to be. There's some artifacts from the Mercury program back in the 60s that will remain and be kind of permanently preserved. But yeah, I would be lying if I said it wasn't going to be tough to make sure that we can build up that capability very, very quickly to support launch when we need to.
No, many people hear that the fact that preservation is part of that key thing that you said, that's so important to know, but also exciting that, this once important pad will open up this new era with a new vehicle. Are you looking currently expanding to other pads at the Cape or Vandenberg at all, or is it all focused on Cape for now with one site, and then we'll see where we go in the future?
I'll say we're in conversations with the different federal range entities. So Vandenberg, obviously the Cape, and then others. We don't want the pad to be the bottleneck. So early flights will happen from LC-14 to the Cape. That's absolutely the case, but we're also considering expanding to other locations and other pads.
What's it like been going through all that regulatory process, working Space Force, the governments? You're going through your EA. We've all been watching closely as Starship's done it. But what's your guys' experience been like? And have there been some surprising hurdles or roadblocks that you've come across?
I think we're just getting started. I think I would say it's been very encouraging because lots of folks at all those different entities genuinely want exciting capabilities to be successful. And I think we've been able to show Space Force and others that we have a really unique and exciting capability that we can bring to fruition. I think that they're excited about that. So of course, there's a lot of paperwork such that we can do things in a way that is safe, sustainable, doesn't kill a bunch of habitat, isn't going to wreak havoc on airlines' flight paths, right? And so that's a lot of work, but so far, I think the interactions we've had have been quite positive.
That's great to hear. I know we're seeing lots of that changing of regulation as commercial space becomes more regular, I guess we could say, for it. Looking at the last couple months of this year and into next year, what can we kind of all look forward to publicly seeing? I know there's a lot going on behind the scenes that won't be.
Yeah, I think the most exciting big milestone is our stage 1 engine hot fire, which looking forward to early next year. So we'll share some video of that, I'm sure, on the socials once that occurs. That's I think, biggest near-term technical milestone. We'll also share more. So we are currently in Kent, Washington. We have I think it's a 22,000 square foot facility where we've done all of our manufacturing. We've been here for a little over 2 years. When we moved in, it felt huge. Now it feels tiny. It's too crowded, right? So we've got to expand. We've already outgrown it. And so remaining in Kent, just down the road, we have a much larger facility. It's about 9 times the size. I think 170,000 square feet. And so we'll be sharing, I think, more about that in the near future, and maybe some large stage 1 structures being built in there. And then, we're looking after now sort of we've proven some capability, I think, looking for, larger government contracts and larger commercial sort of satellite deployment contracts that in the next few months, I'm hopeful we'll be able to announce.
So how does that work starting to compete for those contracts with really only just having done a hop test? We've seen this before, but how do you present a vehicle that we haven't really even seen to these entities?
It's a great question. It's hard to do, right? I think folks who are out, whether they're commercial or government, they can look at SpaceX, who's launching once every 4 days or something like that, and say, look, like, proof's in the pudding there. What Stoke is doing is exciting, but we're certainly not doing what SpaceX is doing on that front.
Not yet.
not yet. And I think, what it boils down to is it's my job to go out and talk to all the folks who need to launch satellite constellations. And it's clear from those conversations there is a coming dearth in supply of launch. I think it's going to be a lot worse than most people think. It'll be very, very hard to get to space. And what you can point at from our perspective at Stoke is, look, we have executed and done every major milestone when we said we were going to do it. And that's rare for space companies. And I think it's really because of what we talked about earlier. It's A, talent, and B, vertical integration that we've been able to do that. And so I think as we talk to some of these constellation operators, we can say, look, there is a dearth in supply. We are executing unlike any rocket company in history, and there's quantitative evidence for that. And we're a very good horse to bet on. And I think those companies that do bet on us will be successful in a few years in deploying constellations and generating that revenue. So, we have those conversations with customers. We've been able to execute, multi-launch services agreements with some of them, and I hope to do more and announce more in the near future.
Sounds like it's an exciting time at Stoke, starting to get ready with those contracts, but also expanding into a much, much larger facility, which we're excited to learn more about as that progresses. Well, Devon, I thank you for your time. I know you guys are all busy and appreciate the insights into it. We'll be following closely, and any way we can support and help share your story, please let us know, because we're I'll say the pun. My community wants me to. We're stoked about you guys. So
I love it.
You got to say it. Everyone's saying it. But I appreciate your time, Devon, and we'll stay connected.
Hey, Zach, I'm stoked too. I appreciate it. Thank you so much for having me. Really appreciate the opportunity to chat with you and get the word out to your network. So really enjoyed it. Thank you so much. And I would love to stay in touch and do it again soon.
Sounds great. Thank you so much, Devon. Have a great day.